this conference. So I want to apologize, first of all, for the lack of coffee. This is something that we will fix in the next few days of the conference. There will be a coffee break at 10:45, so you can hold out until then. But we'll have coffee and snacks available at that point. And it's a real pleasure to welcome you all here. This is the third conference we've had on the foundations of quantum field theory. Wayne and I organized the first one in 2010. We held one in 2019, and so it's great to return to the theme, and there's so much interesting work to be done in these areas. And I want to just briefly thank my co-organizers, Dorian Fraser and Mike Miller, for helping put this together, and for Kate Sinclair, the administrative officer at the Rotman Institute, who's been handling all the logistics for the conference, and for Yishen, who was off at the moment in search of coffee on campus, who's helping lead a group of graduate students who's helping with the organization as well. And finally, we're funded by SHIRT, so I want to thank SHIRT for awarding us funding. And without further ado, I want to turn it over to Mike Miller to chair the sessions today, who will introduce our first speaker.
Great, thanks, Chris. So I'll be brief. Our first talk will be by Noel Swanson, coming from the University of Delaware, on prospects for wave functional interpretations of QFT.
We should say something about the change of schedule, because I don't know that everybody...
Sorry. So there was one kind of travel mishap, which means that one of the speakers will not be here. That's Porter Williams. So everything on today's schedule has just been shifted forward one talk, and will end one. The discussion will kind of occupy the position of the final talk officially listed on the schedule, and will adjourn an hour and a half early today, with respect to what's up on the website. Okay. But otherwise, the order remains the same. The first talk is just slipped up today. Okay. So without further ado, take it away, Noel, and we'll go for 45 minutes, and then there'll be 30 minutes of questions.
Great. Thank you for inviting me. Bummed to lose my opener. I was really counting on Porter to do a lot of hard work, and then I was going to write it in conceptual confusion. So unfortunately, this is going to have to be the introduction to the topic for today, which is something like, what is a quantum field? I also doubly apologize because it's going to have to be a talk by me without coffee, so please bear with me. Okay, so the kind of view I'm going to look at today is a sort of partial answer to the question, what is a quantum field theory? It's an answer that essentially says it's very similar to non-relativistic quantum mechanics. We think of non-relativistic quantum mechanics as describing superpositions of classical particle states. Quantum field theory is like that. It just describes superpositions of classical field states. There are various arguments against this sort of view. I'm going to try to rebut at least some of them, and hopefully by the end convince you that the prospects for wave functional interpretations are a bit better than they may have seemed over the past decades. So I'm going to start with a puzzle. This is the sort of thing that probably has occurred to almost all of us. At some point we learned about quantum field theory, and I suspect that many of us are still sort of in the grips of it, except for maybe David. If you start with something that you have at least reasonably clear grip on the sort of metaphysics of, something like a nice classical scalar field, you have the Klein-Gordon field, which assigns real numbers to points in the cosmic space-time. It satisfies a relativistic wave equation, the Klein-Gordon equation. This is the kind of thing we can make sense of, right? We're assigning numbers that represent some kind of determinate property to space-time points, satisfy some nice differential equations, or reasonably nice. Let's not worry so much about that. Then we try to turn this thing into a quantum piece. And the standard way to do it is second quantization. And here's a kind of rough recipe highlighting some familiar, maybe some less familiar parts of the story. At least a standard way to do it. The first thing you do is break relativistic invariance and choose a 3+1 foliation, which allows you to choose solutions to the Klein-Gordon equation on some hypersurface. And then you can introduce conjugate momentum fields. There's a sort of fancier formal definition, but in the Klein-Gordon field case, this just turns out to be the partial derivative of the field variables with respect to your sort of privileged time coordinate. Then once you have pairs of fields and classical fields and conjugate momentum fields on a hypersurface, you choose some natural symplectic form. And then there is a bit of funniness, because eventually you want to turn this into a quantum theory, so you're going to choose a complex structure on the set of spatial solutions, and it turns out there's actually a lot of free choice here. complex structure, one that seems nice and natural. And in this case, there's some natural ones to choose. Then things get fun. You start replacing variables with operators, and of course, you want to satisfy various constraints. So, for example, you might enforce equal time canonical commutation relations. Plus, you want the classical Hamiltonian form to be preserved in the quantum case. And then finally, you're going to look for a representation of all of this stuff on some Hilbert space. The standard one is Fock space, which of course looks like that lovely direct sum of sectors consisting of vacuum sector, one particle sector, two particle sector, etc. Okay, so this is the standard story. Now the question that most of us have probably asked at some point is, you learn this stuff in a graduate QFT course, and then you're like, wait a minute, what happened to the fields? We started with something that looked like a field theory, and we wound up with something that looks more like a particle theory. Our sort of initial intuitions about this field-like object have sort of disappeared behind a kind of mathematical veil. And there's at least three sort of things to point to here that seem kind of weird. First of all, our classical field variables, which we thought of as assigning a real number to a point in space-time, which is kind of some kind of determinate physical property, has now been replaced by an operator, the kind of thing that in quantum theory represents a determinable physical quantity rather than a determinate property. Right? We have to specify a state and do some kind of experiment to figure out what the field value now is. We've got this sort of determinable located at some region of space. And of course, it's not located at a point for various reasons. We've got to smear these things with test functions. And so at best, they're associated with arbitrarily small compact regions, perhaps. Plus, there's also this sort of weird middleman, right? It's not like we, at least in this sort of framework, we're not assigning operators directly to regions. We're pairing them with test functions that might have nice support properties in a particular region. And then, of course, last but not least, the actual quantum state space we end up with is Fock space, which is most naturally thought of as a state space where the states are described as superpositions of quanta or particle-like states. And so we've lost our, at least our intuitive picture of the classical field here. Of course, with a bit of digging, we can actually find an equivalent picture of what's going on that does look more field theoretic. For instance, field quantization. And the steps are essentially the same. 1 through 4 are essentially the same. The trick is at the very end, rather than trying to find a representation of all of our data on Fock space, we find a representation on an alternative Hilbert space, which is usually called wave functional space. And the key here is we can think of wave functional space as something like the Schrodinger picture of non-relativistic quantum mechanics. Right? So we have an L2 space over some kind of configuration space. This is going to be, at least at first pass, a space of classical Klein-Gordon solutions on some hypersurface sigma. And then we've got some measure here, D, which we'd like to be the big measure, but of course things aren't so nice. It's not going to be the big measure. But the thought is, in this kind of wave functional space, we can interpret the states as wave functionals that assign some classical field configuration, some complex number. Right? So it's akin to assigning some classical particle configuration, some complex number of a wave function representation over position space, over particles. But here we have essentially a wave function representation over classical field configuration space. So here's a kind of characterization of what might go into a wave functional interpretation of QFT. This is coming from papers by Nick Huggett and James Baker. The slogan is that quantum field theory describes superpositions of classical field configurations. The local field operators are going to represent fundamental physical quantities, and wave functionals specify possible field configurations. Okay, so here are some examples, certainly not exhaustive, of this strategy being implemented in physics literature. There's a kind of rigorous form of wave functional representations that Siegel introduces back, I think, in the mid-50s, and then he uses them in the 60s and 70s to start developing ideas for like real-time functional integral constructive quantum field theory. There's an interesting paper by Jacqui from the late 80s called Schrödinger Picture Analysis of Bosons and Fermions. This Hatfield book from 1992 is one of the few textbooks that actually kind of develops things from a wave functional perspective, which is interesting. The same year, Siegel collaborates with Baez and Zhao and writes a kind of summary of what went right and what didn't go right in the sort of earlier kind of constructive program that used wave functional spaces. And this is sort of the source that a lot of kind of contemporary philosophical discussions point to when they talk about rigorous versions of wave functional interpretations. And then more recently, there's been some work on using wave functional representations in curved space-time settings. But all is not well and good. In 2009, Dave Baker writes a paper where he points out that many of the arguments for or against particle interpretations of quantum field theory can also be applied to wave functional interpretations, or at least the standard wave functional interpretation. And the key is this first bit. Baker says, but where this interpretation succeeds, it does so precisely because wave functional space is equivalent in a mathematically linear sense to Fock space that represents states of particle configuration. And so Dave lifts some arguments against the particle configuration or against the particle interpretations to arguments against field interpretations, and he introduces at least another kind of argument as well. Okay, so here are the three main arguments in Baker's paper. The first argument comes from the Unruh effect. The rough idea is that inertial and accelerated observers in a cosmic vacuum end up using unitarily inequivalent wave functional representations, just like they use unitarily inequivalent Fock space representations. And Baker thinks the upshot is they're going to disagree about the field content. This is going to pose a certain kind of problem for wave functional interpretation. The second argument is a new one. This is not lifted directly from the arguments against particle interpretations. But in cases of spontaneous symmetry breaking, Baker thinks a certain physically contingent process turns out to determine which quantities are the field operators in the wave functional interpretation. And the way he's pitching it, field operators are supposed to be fundamental quantities. And so this turns out to be the sort of odd situation where which quantities are fundamental end up being determined by a physically contingent process, which seems metaphysically suspect. So Baker's conclusion is that we can't think of the field operators as representing fundamental quantities the way the wave functional interpreter wants to. There's a variation on this argument that uses spontaneous symmetry breaking in coherent states that introduces a couple of additional wrinkles, but I think the main core idea comes from the sort of early version of the argument. And if I'm right about what's going on here, it's the same kind of reply to both. So I'm not going to go into the other version unless people really want to talk about it in the question session. Okay, so the last argument is another lifted particle argument, right? In this case, Hogg's theorem is going to rule out modeling interacting quantum field theories on Fock space. And so if the wave functional representations are unitarily equivalent to Fock representations, it's going to rule out representing them on wave functional spaces as well. So these are Dave's three arguments. We're going to look at them in more detail in a bit. But this gives you a sense of where it's coming from. So we're going to have a quick aside, a couple of notes about mathematical rigor here, because part of this debate gets driven by worries about mathematical rigor. So there are corners of the foundations of QFT literature where people are less worried about rigor. And it's interesting because in those parts, people are perfectly happy to talk about wave functional representation. So part of the problem here turns out to be like, how do we actually do all this stuff rigorously? And there's a kind of, I think, for those of us that sort of really worry about issues of rigor, I think reading Dave's paper causes us to furrow our brows a bit and get seriously concerned about the ability to think of quantum field as a superposition of classical fields. But hopefully by the end of the day, we'll maybe be feel a bit less furrowed. Okay, so if we dig in and look at either the early Siegel stuff, or the Bayes book, or the more recent kind of curved space-time work, it turns out that our sort of initial glib picture of, yeah, just do something like the Schrodinger representation, but have wave functionals on a space of field configurations, can't be implemented sort of maybe directly in the most obvious way you want. There's at least sort of 3 wrinkles that have to be considered. First of all, right out of the get-go, you can't just take all solutions to the Klein-Gordon equation on some hypersurface and treat that as your space of field configurations. You typically have to impose some kind of boundary conditions that say things fall off sufficiently fast at station infinity, so you're looking at solutions of compact support or fast decrease or something. And again, usually this is kind of left open, like we're going to encounter various integrals, and at some point you need those integrals to converge, so you have to impose some sufficient fall-off condition. And it's usually either compact support or fast decrease. The second wrinkle, which we'll talk about in a second, is that you end up replacing in the end, after like all the dust settles and you've constructed this thing, you end up replacing what you might have thought of as the space of classical field configurations with nice boundary conditions with distributions thereof. So you've kind of already smeared things at the classical level. You've gone from functions on your real value functions on your hypersurface to functionals on that hypersurface. And this causes some people to worry. And then the last thing, which usually creates the most sort of technical complications, is that there's no translation invariant measure on an infinite dimensional Hilbert space, or actually mnemonic space for that matter. So, you know, if we thought that we could do this using the Lebesgue measure, it turns out the Lebesgue measure is not well defined, but find some other suitable measure. And the standard one that's used, at least in the real wave representation construction here, is this Gaussian measure that's associated with something called the isonormal probability distribution. It's not translation invariant, it's unitarily invariant. One of the weird things about it is it's not countably additive, and so you actually have to spend a whole bunch of time developing some analog of Lebesgue integration theory here, which is what sort of sucks up most of the pages of the Bayes-L. But you can do it, and then that's sort of the eventual sort of formal replacement for Lebesgue. Just to dive into this in a little more detail, one kind of nice way to think about what the Gaussian measure is doing is by stepping back and thinking about a one-dimensional quantum harmonic oscillator. If we think about this thing in the position representation, right, we've got L2 over R with our Lebesgue measure dq. If we think of what wave functional or wave function describes the ground state here, it's going to look like a Gaussian, right? E to the minus q2 over 2. Here's the form that the momentum operators take in this representation, right? They look like differentiation. So this should be relatively familiar, but we can actually do something kind of weird. Rather than thinking of the wave function as a Gaussian over this space, we can sort of build the Gaussian character of the ground state into the measure. And so we could instead opt for this Gaussian measure here, which is defined as e to the minus q2 times the Lebesgue measure. This gives us a different measure space. And in this measure space, the ground state just looks like a constant function. And interestingly, our momentum operators have picked up this sort of additional multiplicative term here. And in this case, the two representations are unitarily equivalent. So anything you can do in one, you can do in the other, and there's a nice translation back and forth. Right, so to motivate the Gaussian measure in the infinite dimensional case, think of this example in the background. When we look at the Klein-Gordon field, formally, right, non-rigorously, essentially what we want to do is take this thing here, which you would think of as the naive Lebesgue measure over field configuration. multiply it by this Gaussian, which is defined with respect to this beta or B operator, which, if you look at its form, this is what the Laplacian. So it's essentially, this looks like the Klein-Gordon operator, but you pulled out the time part, right? So this is going to be frame dependent. It's going to depend on your division of space, or your division of space-time into space and time coordinates here. So again, technically this doesn't make sense because this bit doesn't make sense. But if it were definable, indeed, you can do this on like large dimensional Hilbert spaces, then take some kind of appropriate limit and show that this thing converges. What you end up with is intuitively sort of a Gaussian that's corresponding to the form of the vacuum state or the ground state times your naive Lebesgue. And the same sort of thing happens here that happened in the oscillator case. Your momentum operators pick up this additional multiplicative factor, which depends on V. Now, one thing to note is that if you think back to the original quantization recipe, there's this step where we picked a complex structure that was compatible with the symplectic form. The standard complex structure that's sort of chosen by an inertial observer here, who's divided up space and time in this way, can be written like this. And so again, the B operator appears in standard form for complex structure. So the moral here to keep in mind in the background is that both the Gaussian measure and the momentum operators in this wave functional representation ultimately depend on the choice of complex structure. And so when we get to the point where choosing different complex structures give rise to unitarily inequivalent representations, this is where the choice matters. One other thing I want to say, just to kind of maybe make the transition from sort of intuitive configuration space of nice solutions to the Klein-Gordon equation on some hypersurface to distributions a little bit less fishy. So basically say that, look, this is almost exactly the same move that we make when we want to represent position eigenstates in non-relativistic quantities, right? If we think about trying to represent unbounded position and momentum operators in non-relativistic quantum mechanics, right, the position eigenstates are not going to be vectors in our L2 space, but what we have is something like a nice rigged Hilbert space structure, where if you look at the actual domain of your unbounded position and momentum operators, they don't act on the entire L2 space, they act on some dense subspace. Indeed, this is going to be nuclear space. And if that's the case, what you can do is you can show that there's a nice embedding of this into your L2 space, and then there's actually a nice embedding of your L2 space into this larger space, which can be identified with the spacing antilinear functionals on S. And then, once you've done that, your position eigenstates, if you will, your Kets or your position delta function, can be identified with vectors in this enveloping space. And this thing isn't going to be a well-behaved Hilbert space, it's only a partial inner product space, but it's naturally associated with the embedding of S into your L2 space. And so the claim is essentially the exact same thing is going on in field case, where you've got a representation ultimately of your field operators and your conjugate momentum operators on some dense subspace of this L2 space. And the states that would represent states of like determinate, sharp, classical field configurations aren't going to be vectors of this space. They're going to be associated with generalized states or Kets that live in the space of antilinear functionals on S. And that's what motivates the switch from this configuration space to distribution. So thus, if you're metaphysically worried about this, you should be worried about the same move in particle non-relativistic quantum Okay, so let's return to Baker. So Baker's first argument is based on the Unruh effect. Here's a picture of the situation from Halverson and Clifton's paper on the subject. You've got one observer, Minkowski, who's moving inertially. Minkowski foliates spacetime into orthogonal hypersurfaces as a preferred time variable t. Everything is well and good. Then Minkowski's friend Riddler is traveling, or rather constantly accelerating. So Riddler is traveling on this curved trajectory here. Riddler has a different notion, a different natural notion of time evolution. S. We're going to foliate space-time up different hypersurfaces in a natural way. And if we do the following sort of thing, if we consider, say, the algebra of Weyl operators on this wedge region, because it turns out that the Riddler observer is causally confined to this wedge, which sort of limits how much information they can gather about the global space-time state. And we look at two different representations of this algebra. One generated by sort of natural vacuum state for the Riddler observer, and one generated by the restriction of the Minkowski vacuum to the wedge. We end up with unitarily inequivalent representations that are disjoint. And one way this manifests itself is that the Riddler observer and the Minkowski observer have different total number operators. In fact, one number operator is not even defined on the other's representation and vice versa. But there are ways of interpreting the expectation value of these operators in the other representation, and roughly those recipes say, for example, for the Riddler observer, in the Minkowski vacuum state, the probability that the Riddler's number operator assigns some finite number is 0. And so one way of interpreting this is that the Riddler observer sees infinitely many particles in the Minkowski vacuum. Moreover, these are going to be thermally distributed. There's a temperature, right? The Unruh temperature associated with this. This is the sort of standard picture of the effect. Okay, so Baker points out that there's sort of immediate corollary here, which is that if the standard real wave representation is unitarily equivalent to Fock representation, then because the Minkowski and Riddler observers have unitarily inequivalent Fock representations, they're going to have unitarily inequivalent wave functional representations, real wave representations. Dave thinks that the field position is a little bit better off here because the two representations are actually generated by the same field operators. Right? These guys are the generators of the corresponding Weyl unitaries. They're the same for both the Riddler representation and the Minkowski representation. Where the two observers disagree is about what the conjugate momentum operators are. And indeed, they have inequivalent conjugate momentum fields. And this ultimately is traced back to they have different choices of complex structure. And so Baker's conclusion is that maybe the field interpretation is in better shape than the particle interpretation, but it's only so if you deny the physical significance of the field conjugate momentum. I think this is a bit too fast, right? For one thing, we're thinking in terms of a 3+1 foliation, and so insofar as, from that perspective, the conjugate momentum operators are going to be a kind of frame-dependent, emergent object, right? You're taking partial derivatives with respect to different time parameters. T or S equals to the inverse tangent, not tangent, of T over X for Riddler's notion of time. Right, so just from this at the sort of classical level, before you quantize anything, you might think, look, we have reasons to think that the conjugate momentum operators really shouldn't be treated as fundamental quantities by the wave functional interpretation. They're a kind of emergent frame-dependent quantity. And the fact that the Minkowski and Riddler observers agree about field operators means there's a kind of deep agreement about the fundamental quantity. So we don't have to actually deny the physical significance. We can just ascribe to them a kind of frame-dependent emergent character. I think this is too quick, though, right? There's a deeper problem, which is that even if you think the two observers agree about what the fundamental quantities are, they still assign them in a kind of a deep, or at least apparently deep sense, incompatible boundary conditions, right? The Minkowski observer assigns temperature 0 to the state, and the Riddler observer assigns some non-zero temperature. These can be chalked up to be incompatible boundary conditions are associated with disjoint KMS states. So looking at the clock here. So I think there's a couple of ways you might try to respond to this. I think Baker is sympathetic to option 1, where you try to argue that both observers are right, and that this disagreement in boundary conditions is really, again, a kind of perspectival disagreement, like the disagreement about the emergent momentum quantities. So that's one way you might try to develop this argument. Another option is to sort of say that there's reasons for privileging one observer's perspective rather than the other, and probably the most obvious one, the privilege is the Minkowski observer. There's various arguments in the literature of the effect that Minkowski observers view should be privileged for some reason. Here's a recent one by Huppels and Burke, which is kind of interesting because their claim is that when you actually think about what the Riddler observer is measuring, there's a kind of correction factor, and that the temperature they assign to the vacuum state will actually be 0. And the thought here is something like, if what's going on is the Riddler observer is seeing a bath of particles that are thermally distributed, and that's what's responsible for the temperature, it's a really kind of funny effect. Right, the Tollman-Ehrenfest theorem says that if you've got a bath of particles, the temperature should be, and you've got an accelerating observer, the temperature should be position dependent in a certain kind of way. And you don't actually see that for at least the standard calculations for the unrubbed temperature. Oftentimes, you kind of regain position dependence by inserting a kind of correction factor in, but apparently it's by hand. And Huppels and Burke argue that this is sort of made further weird by the fact that if you look for other sorts of extensive quantities like pressure, those are going to have 0 expectation value for the Riddler observer. So there's a kind of disconnect between what we think of as the properties for a relativistic particle bath and whatever the Riddler observer is experiencing. Moreover, if you look at the way you'd actually model a thermometer with some kind of probe that the Riddler observer carries, it's going to couple to the vacuum, and if it's accelerating, the argument goes, it doesn't just exchange thermal heat with the vacuum, it also exchanges mechanical energy. And ultimately, their argument is that the temperature that's measured is the result of this mechanical energy that is exchanged between the probe and the vacuum. So they think what you need to do is factor out that sort of mechanical energy correction factor. When you do that, you get temperature 0. So if Huppels and Burke are right, then the boundary conditions that the Riddler observer assigns are actually sort of not the right physical boundary conditions. And once corrected, they align with what Minkowski observers. Okay. So let's look at Dave's second argument here, spontaneous symmetry breaking. Here, Baker considers a massless Klein-Gordon model. This displays a certain kind of simple kind of spontaneous symmetry breaking. In the classical case, we take a solution to the massless Klein-Gordon equation, and then add some constant eta to it, we also get a solution. And it turns out that when you sort of implement this thing algebraically in the quantum case, this sort of add a constant everywhere map is implemented by an automorphism of the Weyl algebra that you use for dynamics, so it looks like symmetry in the quantum case. However, it's a spontaneously broken symmetry, so if we define a family of vacuum states by taking our original eta equals 0 vacuum state and combining it with the action of the automorphism on the algebra like this, we get several different states, and we construct representations using the GNS construction, we get unitarily inequivalent GNS representations. Now, unlike the Rindler example, each of these representations actually have different field operators, right? So the operators that play the role of the fields in the original representation are replaced by these primed guys that essentially look like the operator version of adding a constant operator to this smeared operator. Eta times the constant operator. Now, one thing that's sort of an important note here for Baker's argument is that even though which operators are the field operators differs from vacuum representation to vacuum representation, mathematically, the different field operators are still well-defined operators in each space. It's just that which ones play the role of the field operators differ. Right, so here's Baker's symmetry breaking argument. The smeared fields are fundamental physical quantities according to the wave functional interpretation. However, the outcome of spontaneous symmetry breaking in this case determines which quantities are fields. Since the outcome of spontaneous symmetry breaking is physically contingent, the outcome is physically contingent because it depends on initial conditions. And then the last bit is sort of a metaphysical posit. Baker thinks that which quantities are fundamental, if they're instantiated, is a physically necessary fact. In this case, that F4 is broken, assuming we treat the field operators as fundamental physical quantities. So it seems like if we want to hold on to the metaphysical posit, we've got to give up on the idea that the field operators are fundamental physical quantities. Which seems at odds with again, I think this is sort of too quick. I think there's a kind of loophole in the background that we might be able to exploit. Right, if you think about the classical case for a second, we have spontaneous symmetry breaking, but no obvious problem, right? We're replacing some field configuration phi with phi plus a constant everywhere, right? This intuitively looks like the same field, just with different global boundary conditions. What gets weird is that when we move to the quantum case, right, we've replaced our field configuration variables with operators. So we've switched from determinate physical properties to determinable quantities. And now the same kind of symmetry seems to be taking us from the fundamental quantities in one representation to the fundamental quantities in a different representation, which are different operators. And so unlike the classical case, which appears directly to be same field, different boundary conditions, here we've got something like different fields in the quantum spontaneous symmetry breaking case. Right, but here's an important observation. The comparison seems a little bit weird because in the classical case, what we have is symmetry that acts on determinate field configurations. And in the quantum case, a symmetry that's acting on determinable field quantities, which play a different sort of role in the theory. So I'm going to suggest an alternative interpretation, according to which both of these pictures actually describe the same fields with different boundary conditions. It's just that the classical case is operating with something like a Schrodinger picture of symmetries. And the quantum case is operating with the Heisenberg. Right? So what do I mean by this? We have to step back and think, what's symmetry in quantum field theory? Anyways, the kind of standard Heisenberg picture that we typically operate with is we think of a symmetry as an automorphism of the algebraic structure, of the algebra of quantities. It's a Jordan isomorphism, say, of the Weyl algebra. But when we do this, we hold fixed the states. So in particular, the key upshot is this, right? We can use the same state functional omega to represent different vacuum states by applying it to different algebras, right? The original Weyl algebra versus its symmetry transformed counterpart. Right, so the thought here is that this is quite naturally thought of as describing different vacuum states with different boundary conditions. It's just that we're sort of representing different boundary conditions by changing which operators represent the fields rather than changing the state itself. If we really wanted to, we could sort of move to what you might call a Schrodinger picture of symmetries here, where instead of an isomorphism of the algebra, you've got an isomorphism of the state space, right? The space of normalized, complex, linear functionals on the algebra. This is going to this space has a nice geometric structure. It turns out that its automorphisms are going to be affine homeomorphisms. And from this standpoint, the symmetry is going to take you from state to state in the state space, while your algebra of quantities remain in space. And so here you're going to use different state functionals, omega versus its symmetry transform counterpart, to represent different vacuum states applied to the same algebra. Gothic script. And of course, there's like a nice natural correspondence between the Heisenberg-Schrodinger picture of symmetries here. It justifies this law. Right, so here's a kind of revised version of Baker's argument. I think F1 and F2 need to be modified in light of the fact that we're operating with the Heisenberg picture of symmetries, at least in the standard kind of presentations of this stuff. F1 should read, the smear field operators represent fundamental physical quantities according to the wave functional interpretation, right? They are not fundamental physical quantities, but they represent them. And what the outcome of spontaneous symmetry breaking determines is which operators represent these quantities. And once you make these changes, you can hold on to the physical positive. The thought being that we have our different states with different boundary conditions represented by the same functional applied to different operators. Different operators represent the same fields. We started like 5 minutes late. Okay. Let me take 5 quick minutes to say something about interactions. Here I think things are a little bit trickier. Right, so corollary of Hogg's theorem, right? Any irreducible representation of equal time computation relations for interacting fields is going to be unitarily inequivalent to any Fock representation for any finite time. Baker points out the same is going to be true for any real wave representation equivalent to a Fock representation. And he traces the kind of deep problem, kind of explaining this back to an argument from Gordon Fraser. Roughly the thought is that, remember there's a difference, or rather there's a key point where we choose a complex structure. And we can often think of the complex structure as being associated with the splitting of the field solutions into positive and negative frequency components. However, in an interacting theory, there's not going to be a Lorentz covariant frequency splitting, roughly because you're not going to have like a rest frame mass condition that guarantees the vectors that correspond to the sort of basic solutions are always going to be time-weighted. So you're going to have solutions that are built from, or potentially built from, vectors that have space-like components. And so Lorentz transformations will look this up. And since you can think of a complex structure as defining a splitting, the thought is there should be no Lorentz covariant complex structure either, right? So here's, like in the standard case, where you've chosen some splitting into positive and negative frequency spaces, you can just define the complex structure as I times the positive part minus I times the negative part, or vice versa for that matter. And the thought here is, you can also go in the reverse direction. You can define the splitting in terms of complex form, complex structure. I think there's various reasons to, yes, I think the basic idea that the standard real wave representations can't be homes for interacting quantum field theories is true, or different, larger than the wave functional representations that Baez et al. Construct. Of course, the trick here is we don't yet know quite how to make physical, or rather not physical, but mathematically rigorous sense of these things. I also think that the role that the complex structure plays in the Fock space representation is somewhat different than it plays in the wave functional representation. Right in the Fock space representation, the complex structure is important for defining the splitting, or not defining the splitting, is related to the splitting which is already given. And that corresponds to a way to identify a space of positive frequency solutions, which you ultimately identify with the one particle subspace. So the way you identify the difference between particles and antiparticles turns out to be sensitive to this complex structure. So it seems like the nature of particles is going to be sensitive to the complex structure in a way that it's not so obvious, or that's not going to so obviously carry over to the wave functional case, where it plays a sort of much less direct role in defining the Gaussian measure and the form of the momentum operators in the wave functional representation. There's also some thoughts that there may be alternate ways to motivate the choice of a complex structure. I mean, look at curved space-time settings. You don't have in general, you're not going to have a nice positive-negative frequency splitting of the space of solutions, even in the free case. In those cases, folks have proposed other sorts of principles motivating the choice of a complex structure. So here's one from Ashtekar and Magnolia in 1975. Essentially, the thought is you take a classical solution of the Klein-Gordon equation, compute its stress energy tensor, and then integrate to find the energy, and set that equal to the corresponding energy of the one particle state associated with that solution and the one particle Hamiltonian. And that turns out to pick out the same complex structure in the inertial case. Last but not least, there are some limited go results. At the end of the Baez and Siegel book, you actually have constructions of non-trivial, non-linear quantum field theories in 2 dimensions that use the real wave representation. But of course, if you squint carefully at least these constructions, the ones they explicitly give are on spaces where you've got either space has been compactified or you've got some spatial cutoff. And so the kinds of worries that come from Hogg's theorem that Doreen raises aren't going to apply there. So they're very limited go results in that respect. And I should stop because I've run over time, but look forward to questions.
Okay, so I'll get a cue going. If you'd like to ask a question, please raise your hand and keep it raised until I acknowledge you. Let's start with David.
I want to worry a little bit about quite what we mean by wave function representation, because it feels to me there's 2 slightly different things going on. So if you think about the analogy that started this with, we don't actually do particle quantum mechanics, this is field quantum mechanics. But of course, we could do particle quantum mechanics without being committed to prioritizing the position representation and the interpretation of quantum states as complex fields on configuration space. There's a whole bunch of different ways we can go there. A lot of them are much more pluralistic about the third basis. And I guess I'm interested in how much you think all of this concerns the specific idea that what we're doing is quantum field theory of something with field observables in the field configuration representation, rather than the kind of prior question, are we doing the metaphysics of a field theory predominantly characterized by localizable field operators versus the metaphysics of a particle theory characterized by a Fock space structure or something. It feels like a lot of this speaks more to that prior question than the more specific idea of wave functions.
Yeah, so I guess one question here is does the wave functional interpretation require privileging the field configuration representation the way that you might privilege the position representation in non-wave? So I think there's the good news is I think we can be ecumenical here. So if you're a fan to interpretations, you have a reason for privileging position in the non-relativistic case. It may very well be the case that you have similar or maybe slightly variant reasons for privileging configuration space in the field configuration space in the quantum field case. There may be other reasons for privileging the field configuration space that are not tied to a particular interpretation. That's where I'm kind of not so sure about. On the other hand, I see no reason why, if you wanted to be a kind of pluralist and say, look, we're really interested here in something like L2 representations of field operators. There's nothing in principle preventing us from looking for like L2 representations of momentum operators and that kind of thing, in which case you could restore some amount of parity. I mean, I think the upshot is like doing any of this rigorously is like super hard, and like it's taken people like 60 years to sort of chip away and make very tiny progress. And so like the way we can just sort of, you know, liberally write these various representations down in the non-relativistic case, it's like there's no guarantee that any of these things exist that are nice in the quantum field case. And so the thought is just something that, you know, our typical discussions of these topics are so tied to Fock space that I think, you know, as sort of interpreters, we should step back and think a bit more about other possible arenas, but arenas that look more naturally field theoretic in the QFT case. And I mean, to that effect too, I think one thing that does come out of like staring at wave functional interpretations long enough is you start to realize that like a lot of the things, like the boundary conditions in place that give you the real wave representation that happens to be equivalent to the Fock space one, look like you've chosen them specifically to get something equivalent to the Fock space that has a nice particle interpretation. And so you start to think about like a lot of the standing kind of apparently just sort of mathematically nice constraints we have in the background are actually doing real interpretive work of like singling out the field configurations that have nice particle interpretations that maybe are larger sort of zoo things to think about here.
Carlos.
I think the question is very similar to David. If I got the questions right. I was very confused by your presentation. I sort of agreed with everything you said, but I didn't understand what you were talking about exactly. So I shifted between two attitudes. One is that yes, I agree that's cleaning up this Baker objections make no sense. Perfect your answer. And the other, it's what you talk about, what is fundamental. So what I'm confused is the distinction between representation and interpretation. The way I study quantum field theory, it's very much, in a sense, closer to the field representation than the particle representation. And the way I've always thought about this is that in non-relativistic quantum mechanics, non-relativistic quantum mechanics is not about a superposition of different positions of the particle. It's about a system where there are different observables which are different bases. So I can describe the system in one basis or the others, and I know that this is perfectly okay because it corresponds to a different way of interacting with the system. So for instance, if I have an harmonic oscillator, I have the energy basis, and I think about quanta, 1 quanta, 2 quanta, 3 quanta. If I have two harmonic oscillator, I can think of the quanta here and there, or the quanta of the modes, different basis. Or alternatively, I can think I'm measuring the amplitude of my pendulum, and then I have psi of x, and just the basis, or I can have psi of p. So I've always thought that in field theory it's exactly the same thing. And there's a quantity which I have measured, which is a particle number, which is very good because it corresponds to certain things in our detector. There's another quantity I can measure, which is the value of the electric fields near a region, which also can be measured. So are you saying, and that's my double interpretation of it, are you saying, all right, so it's exactly the same in field theory, there are technicalities, there are complications, but this can be worked out, and let's not confuse technicalities about infinities with the fact it's exactly the same thing? Or are you saying, oh no, there's something special, which is the interpretation as the fundamental quantities is the position, the fundamental quantities is the field. In the first case, I'm having with you. The second case, I'm not sure I
Yeah, good. So I think I agree with you more than you think.
Okay, good.
So, yeah. So this talk, one thing that's a little bit weird is that the way Dave uses fundamental in the paper kind of shifts back and forth between like the metaphysician sense of like the quantities that are at the bottom of whatever kind of emergent structure we have that are privileged in some kind of physical sense, and then fundamental in a far more deflationary sense, which is just like physically significant or like perfectly natural or something like that. I don't think I don't certainly want to load too much onto the field operators or fundamental quantities. In fact, I think there's a sense in which that's a kind of mistaken way to think about what the wave functional interpretations, at least at this stage, are up to. For one thing, it seems quite plausible that any actual answer to what are the fundamental in the metaphysician sense quantities here are going to depend on some solution to measurement problem. And what we have here is a kind of like initial story, which is something like, if you think about non-relativistic quantum mechanics for a second, whatever is going on, one of the things that the states in non-relativistic quantum mechanics can be interpreted as assigning superpositions to positions, superpositions to energy, superpositions to other sorts of quantities. And so one thing here, we can think of the wave functional interpretations as a way of recovering the idea that part of what's going on in quantum field theory is we can think of the states as superpositions of classical fields. And there are contexts where that's useful, and it helps us see like the structure of the vacuum state, and there are contexts where it's completely not useful, and for most actual computations it's completely horrendous and not useful, which is probably why, among other things, it's not used very often. But when you talked about like the change of basis stuff, there's actually a nice way to do this. In fact, in the Siegel and Bias, the way they kind of pitch it is, you should think of, in the case where you've got an equivalent Fock space representation and wave functional representation, a real wave representation. The Fock representation diagonalizes the total number operators. The real wave representation diagonalizes the system of field operators at a time. And so it's in that sense, and of course it's more general than the standard like basis of eigenvectors because there are generalized eigenvectors and all that kind of stuff. But that's essentially what's going on, right? You static representation allows you to see the states as superpositions of a particular collection of quantities, or eigenstates of a generalized eigenstates of a particular collection of quantities. I think the tricky thing there is that in the ordinary quantum mechanical case, you get all that kind of like the existence of these bases very quickly for free. And the existence of these representations is not guaranteed. It's not guaranteed that they're going to be nice in the quantum field theory case. I do suspect that there's actually probably fairly I think that there are kind of probably ways to end run around the explicit construction of wave functional representation and say, we know that one exists for the following general reasons, even if I don't know how to write it down. But I'm not totally convinced by those quick arguments. That's another thing.
Yes, I think this is a continuation of the first two questions, but I'm going to form in a very specific way. I don't understand the identification, which is not yours, which also shows up here in these titles, of the wave functional representation with the Schrödinger picture.
Oh, that's quite cool. Okay, yeah. So I mean, the short version is the standard way of constructing these things is to choose a 3+1 division. And so what you end up with are essentially wave functionals that assign field configurations on some hypersurface, a complex number. And so the way the most direct way to interpret that is it's the wave functional of the field at time t.
But I can do that in Fock space as well.
Well, you can split things up into like at a time. Yeah. The thing that's sort of okay, good.
That was my question. I can totally see a Schrödinger picture which uses the Fock space, and I don't see what like makes the wave functional representation more Schrödinger picture like.
Yeah. Yeah, it could just be. That's a good historical question. I'm not sure. So Siegel never refers to it like that.
Yeah.
I think so. So my guess is I think that talk starts to emerge in the 70s when people were applying this stuff Because there, I think like the thoughts of the Fox space constructions on a hyperservice are less direct, and this gives you a way of thinking about how to think of like the state of the field on a hyperservice in a more direct way, which is sort of then back interpret the Fox space representation too. So for example, in this Ashtekar and Magno paper, essentially what they do is they consider a Klein-Gordon field coupled to an external gravitational potential that's like turned on for some finite time, and then ask like what happens in this picture. And it's weird. Essentially, what happens is that the complex structure that's you start out with that's like hyperservice dependent actually changes, and so you've got a changing complex, a time-dependent complex structure. The transformation is given by the Bogoliubov transformation, and they actually think of like the transition function as characterizing the rate of particle production. And my sense is that the way I'm not totally sure about. My sense is that the way they got that construction was by using the tools from this that were not so obvious in the Fox space.
Okay, so it's the time dependent, potentially problematic time dependence of the complex structure, which makes the Schrödinger picture less attractive in Fox space.
Or that
this might lead you to
something
associate
like
the
this.
Schrödinger picture. Okay, but that's yeah.
David, was that a finger on this?
Yeah.
New hand. Okay, so then we have Wayne.
Thank you for this. I like this talk. So I think it's really important to get clear for given quantum field theory of the variety of different Hilbert space representations you have available to you, because they can help you think about different ways, things in different ways. My question, I think, is pretty much been anticipated by David and Carl, because I was going to ask you, what does fundamental physical quantity mean? And I think you've answered it, because at a certain point you said, I don't think there's a answer to that that's independent of approach to the measurement problem. And I think that's right, because the non-controversial core of any quantum field theory is basically sort of operational core. We learn how to associate states with preparation procedures, and how to calculate probabilities, or how to come up with various things. And then if that doesn't privilege any, it doesn't even make sense to ask about what fundamental physical quantity is. But if I wanted to do a hidden variable theory, then I might ask, well, okay, which quantities are going to be, I'm going to be taken to the ones that are definite all the time. And people do try to do quantum field theory versions of like Bohmian theories. Sometimes you have particles that have different positions that don't have a fixed number and pop out out of existence, or sometimes people attempt to have field configurations be the things that are always definite. But I think it'd be better to start saying that, right? Because you were using the phrase throughout, fundamental physical quantity, as if we're supposed to know what it means.
Yeah, so I'm sorry. That's just sort of kind of an artifact of
That's Dave's,
Baker exegesis, I think.
yeah, that's Dave's problem, really.
But I like what you put it, because I think, and this kind of goes back to the response to Carlo and David. Like I think the way to think about this stuff is we're used to having a certain kind of flexibility to look at quantum systems in the non-relativistic case in lots of different ways.
Right.
And at least, school on like textbook QFT and like algebraic QFT, it seems like we're missing some of those pictures in the QFT case. And the thought is, they're there, we have to look harder for them. And then once we do that, then we can ask questions, interpretive questions like, is there a reason to privilege the configuration basis, that kind of thing. I just, in thinking about your question, I just also thought of actually one, I think I just completely buffed that last question. Because it's actually not the Schrödinger picture that they're worried about here, it's the Schrödinger representation. So the thought is the Fox space representation is just not L2 over something like any sort of space. Sure, it's equivalent to it, but it doesn't naturally look like that. So the thought here is that what we have is something like an L2 space over some kind of configuration quantity. So it's the Schrödinger representation, like the classical Schrödinger representation, not the Schrödinger picture.
Okay, because Jakib's paper book is called Schrödinger picture.
Yeah, I think that's just like a terminology.
Okay. Doreen?
Thank you, that was a really nice talk. So I probably actually need to digest the end of this before I can ask this question properly, but we try here. So I like the point you made about spontaneous symmetry breaking and the contrast between the determinate fields that
Yeah, no, so in a certain sense, I think the problem here is deeper, right? I think the second argument essentially like dissolves on the confusion about these two different pictures of symmetry.
Yeah.
I think the question here is, when the real problem for the wave functional interpreter is not that conceptually wave functional interpretations are incompatible with interactions. I think it's that the standard constructions of wave functional interpretations that we have rely heavily on a 3+1 split and the linear structure of the Klein-Gordon equation at various crucial points. And so the two big generalization questions are like, can we construct wave functional representations that don't rely on the linear structure as directly, and or that don't rely on a 3+1 split as directly, and that might help us in the interacting case. And the problem is there's like very little progress that's been made on that. So I think there's still like a kind of serious conceptual worry for the fan of wave functional interpretations, which is that like we don't have very many examples, and it's sort of difficult to see exactly how to extend the examples we have to the interacting case. But in a certain sense, that's sort of everyone's problem. Like, sure, like you have Euclidean functional constructions. I'd like maybe some nice existence proof that like low-dimensional phi-4 theories have a wave functional representation, even if we can't write it down directly or easily, something like that. But that's the sort of I do take it that the challenge from Hogstad is that it does get at the kind of like what the technical complications for constructing these things in a way that the other problems don't. Eduardo.
Hi, yeah, thank you for the talk. Very nice. I have a question related to and again, I mean, the personal perspective here coming in. I do feel like it's very similar to what been asked and discussed, right? That definitely having a measurement theory is what should inspire, in my opinion, should inspire interpretations of what's going on, right? I do understand that the particle interpretation is very associated with a way of seeing QFT that comes from binary physics a lot. I kind of think that the wave function interpretation comes from more like, I want to do something similar to what I do in regular non-relativistic quantum mechanics, and very Copenhagen in kind of spirit, or in a way at least collapse, if not literally, at least inspired by. Why do we discuss this too? It's not a dichotomy in a way. For example, imagine that I give you a measurement theory that is based on measurements that I can do with detectors, like local detectors that are on for a finite amount of time in a finite lab, right? And then I tell you, well, I can write all the predictions that I would do in physics in terms of endpoint functions, correlators of local elements of the local algebra of observables, right? Then maybe the fundamental objects of the theory should be the endpoint functions, or the correlators of the elements of the algebra. Why not? So why I understand that there are extremely good people thinking about what's fundamental and so on, but what couldn't it be in a way simpler, right? I have elements that are very well defined. Those expectation values of those correlation functions of elements of the local algebras, and certainly I would argue that I could explain experiments with that. Even all observations that I can do could be explained in terms of that. So why are not those objects or candidates for fundamental interpretation, or why this dichotomy between a particle versus a wave function, or at least in lieu of a common accepted measurement theory, right, for QFT?
Yeah. Okay. So two things. First of all, I'm not sure if I want to do this right now, but I would push back against. At least I find correlator functions to be like wildly metaphysically confusing. Like,
how come? Yeah, tell me.
If that's this is the way I don't want to go into. I was just going to say that when you look at like the literature on like solving the measurement problem in QFT, in many places you find people talking about wave functional interpretations. Like the Bohmian QFT literature is filled. Everyone talks about wave functional interpretations, and of course they're typically talking about them without the kind of degree of mathematical rigor that people like Baker are worried about. And that's why there's a kind of actually disconnect between like the algebraic QFT literature where people are seriously worried about rigor and like parts of the literature where people are far less worried. But in many, at least the philosophical corners, there are people really like wave functional. But I don't think so. In that case, I don't think that like having wave functional interpretation is like tied to Copenhagen or anything like that. I think it's one thing that's nice about it is since it does look conceptually a bit more like what we're used to in non-relativistic quantum mechanics. It helps make understanding the sort of space of interpretive options from there lifted into QFT perhaps a bit easier. So that's all I'll say about that. I mean, in terms of like interpreting QFT as well, so then the question is like there's lots of other sorts of potential options that don't go this route. I mean, yeah, there are lots of other sort of field-like entities in QFT that we could point to, right? Fields of operators themselves, or fields of expectation values, or fields of two-point values, or things like that. And sure, these are all fields in a kind of mathematical sense of like sufficiently smooth assignments of mathematical objects to points or regions, yada, yada, yada. But I think the thing that sort of makes me balk is when you step back and think about the kind of role that those things play in the theory. They're either too operationalistic for my taste, or I just can't, like, I have a hard time picturing like what a world would be like where the expectation values are the fundamental thing. Like, I can try to think about it, just look at a very weird kind of, it's a very weird kind of field. And I'm happy to think about weird kinds of field theories, but I just think that they're, I mean, a bit weird. Like, I mean, one thing I've worked on is the view that like you've got a field of density operators. That looks weird, but it's still fun to think about, and maybe a way to go.
So I think that then, maybe it's not to discuss later, but I think that we would disagree on what I would call weird, because for me the wave function interpretation is extremely weird.
Yeah, no, I totally agree. And I think, I mean, this goes back to the, kind of the first two questions. Like, I think part of what this stuff does is, if you're used to trying to like figure the story out by having like 2 or 3 standard views on it, but you're ignoring like the other 10 windows that are there that are hard to find, it's worth looking at the other 10 windows.
Was that a finger on this row, or a new question?
It was a thing of the previous one, but it's transforming a question into being one.
Okay, well, so I'm taking us 5 minutes past because we started 5 minutes late, and we have just 2 minutes of additional 5 minutes, and now 3 people in the queue for a second question. So we got through everybody's first question. But David, is your
Yeah.
reasonably quick?
Yeah, I think so. So this specifically on the spontaneous symmetry rating, I'm trying to understand what the supposed concern is about whether our fields are I or phi plus lambda 1. I mean, I can imagine, again, analogously, classical, in quantum particle mechanics, person A says, well, my fundamental observable is the positional observables. 3 xi, yi, zi for, Canada, xi, yi, zi for I equals 1 to n. And then somebody else says, no, actually the fundamental operators in my theory are the operators xi minus minus lambda x, yi minus lambda y, zi minus lambda z. And that looks fairly clearly like a numb disagreement. It's a different way of coordinatizing the same underlying physics. And I mean, I could say this about more radical transformations, but at least in this case, when I'm preserving the spectrum, observing the
It's a very tame.
yeah, why isn't that just conventional? I can describe it as phi or phi plus eta I, whichever I feel like.
Yeah, no, this is good. Yeah, I pressed Dave on this point, and I think it's actually a little unclear to him at this stage. I think his thought was something like, which operators like play the right role in the commutation relations end up being different, and if one was committed to like, this is where it gets a little dicey. Like, if you're thinking of these as like fundamental in the position sense, then that might be important. Like, certain ones are the ones that are there, and everything else is structure from those things. But if you're just thinking of like fundamental and far more like equation, like these are physically significant, like sure these are physically significant, so are these other ones. They satisfy some other more complicated relations, but that's fine.
But I mean, even with my very thick metaphysics hands on, I don't want to be committed as to whether the
Right,
position operator
yeah.
is x or x minus 2.
So there's a whole other thing, like the whole immediate identification of the field operators with fundamental quantities is problematic for all sorts of other reasons, and this is essentially like gauge symmetries, the field operation, gauge invariance. So like, presumably you want to filter Dave's story through some kind of initial like, if you wanted to go for the like, if you wanted to wear the thick metaposition tab, you want to initially filter Dave's story through like additional sieves that help you filter down to whatever you think of as the presumably fundamental classical variables, and then those get transformed into the fundamental quantum variables, although there could be like additional, freedom in the quantum case is not there in the classical case, or vice versa. So that may not be a perfect way to do it. But yeah, I agree with those.
Okay, so with apologies to Wayne and Carlo who are still in the queue, I'm going to draw us to a close here so that we can all get some coffee.
There is coffee outside.
And we'll come back, do you wanna come back in 15 minutes? Just shoot everything 5 minutes after?
We can,
Sorry,
sorry,
for
how
that.
long was the original coffee break?
My guess is 15. I don't know,
Yeah, okay, let's shift it back by, give ourselves a full 15.
Yeah, so we'll meet back at 11:05.